Hi, today I'm going to discuss Einstein-Rosen Podolsky paper in theoretical physics. It's considered to be one of the most important papers in 20th century. So instead of electrons, which they used, I'm going to use socks. So I have two pink socks here. Now in the case of socks, you could wear, each socks to left leg or right leg. It doesn't matter. But to simplify, just call this is for left leg. So I have a L here, and this is for right leg, R. So I have a pink sock, which is left leg, and the other one is right leg. And then I got two white socks. Again, one is left, one is right. So two white socks. And then these two socks, I'm just going to call them green. Green left, green right. Okay, so I got 6 socks here. So I'm going to mix them up. Okay. So I'm going to mix them up, and then I pick 3 of them randomly. Okay, 3 of them randomly. I'm not doing any magic or anything. Just I just pick 3 of them. So I take these 3, the other 3, these 3 I keep, and these other 3 I send far away. I send to faraway country, Iceland or somewhere, or to the moon or someplace far away. Okay, so I send these. Now I have these 3 socks here, and now what I'm going to do, once that is gone to Iceland, now I'm going to check. I got 2 whites here. White up, white right, and white left, and green right. So I got 2 whites here. That means I know that there cannot be any white socks in the other box that I sent to Iceland. Okay, instantaneously I know that. And then I got green right. So I know then other box should have green left. Okay, so magic there. There's no magic. Okay, and then I don't have any pink, so then the other box should have 2 pinks and the green one. It's not a magic. It's so I could keep doing that. As soon as I know what in my box, and then it doesn't matter how far this could be in the other side of the universe. As soon as I measure it, I know exactly what's in the other box. It's not a magic here. It's no big deal. And that's exactly what Einstein said. He said there's no magic here. Making a magic unnecessary. So what was the problem? So instead of socks, we had electrons. We had 2 electrons. One has a spin up, the other one has a spin down. Now, people like Niels Bohr, Schrödinger, Oppenheimer, all those quantum physics guys, Heisenberg, not Oppenheimer. Sorry about that. So they said that let's say this is an electron, spin up electron, and this is a spin down electron. According to them, they don't stay like that. This one changes. This one goes spin up, spin down, spin up, spin down. This one is spin up, spin down, spin up, spin down. And when I send this to faraway country, to Iceland, and then this one keep changing, spin up, spin down, spin up, spin down. And then I make a measurement, and it comes up, spin up. And then according to the quantum physicists, this would send a message to the other one, look, there's a measurement is being made. I have decided to be spin up. You have to be spin down. Immediately message is sent, faster than speed of light, instantaneously. That's what they said. And Einstein said, no, it's not spinning up and down. It just stays the same. Or there's when they were born, this was born right and this was born left. That's how they were born, and this was not going to be right, left, right, left, right, left. It's just going to stay right. And this is going to stay left. And it goes far away. It doesn't matter. If we make a measurement, this is right, the other one is left. That's how they were born. That's how they were created. But the quantum physicists did not like that. They said, now why these quantum physicists, Schrodinger and all those people came up with this idea that these electrons are spin up and spin down, they are moving between those two states. The experiments, especially the double slit experiment, maybe one day I will do that. I did the double slit experiment in my YouTube, but I did not connect that to the Einstein Rosen Podolsky paper. But as per those experiments, especially the double slit experiment, the electrons don't stay in one spin state. They interchange. That's why Schrodinger came up with it. Was confusing. That's why Schrodinger came up with the cat idea. The cat is neither dead nor alive. It's in an in-between state, superposition. When you open it, then it becomes either dead or alive. Until we open it, it's in an in-between state. We don't know. There's a wave function, Schrodinger wave function. And wave function has probabilities. Probability of cat being dead and probability of cat being alive. It's keep changing the probability. There's a probability. So that's why they said that if you take an electron and if it is spin up, it's not just spin up all the time. It's just changing. Spin up, spin down, spin up. Now when we make a measurement, let's say we made the measurement when it is spin down, and the other one, which is in Iceland, we'll get a message from this instantaneously. I am spin down, you have to be spin up. Faster than speed of light. When something is going faster than speed of light, the technical term is non-locality. Now, we know nothing can travel faster than speed of light, but this does. So Einstein didn't agree with that. And he said this, it's like socks, if it is spin up, it stays spin up, like socks. This issue, Einstein died in 1955, I think, and Bohr also, most of these people died in 1950s. The issue was settled in 1965 by a experimental physicist named Ian Bell. He devised an experiment. This is the experiment he devised. So we have 6 socks here. Now if we pick any 3, say I got 2 greens and 1 pink left, or I could get 2 greens and pink right, or I could get 2 greens and white left. I could get 2 greens, and like that I could have different combination of picking 3 socks out of 6. And it's not a complicated mathematics. There are 20 different ways that you can do that. There are 20 different ways. So now he said, how many different ways you can do that with 2 same color socks? So let's say I get 2 greens. So I get 2 greens. How many different ways that I could get 2 greens and something else? So I get 2 greens and white left, one way, 2 greens and white right, second way, 2 greens and pink left, third way, 2 greens and pink right, fourth way, 4 ways. So similarly, I could take 2 pinks and white right, 2 pinks and white left, 2 pinks, green left, 2 pinks, green right. 4 different ways. So 4 and 4, 8. Similarly, I could do with 2 whites and 4 different ways. So there are 12 different ways that we could get 2 socks with the same color out of 20. So there are 12 different ways that we can. This is not magic, this is just very simple. Let's do for 2 whites if you want. 2 whites and green left, one way, 2 whites and 1 green left, one way. 2 whites and green right, second way. 2 rights, pink left, third way. 2 whites, pink right, fourth way. So 4 ways with 2 whites, 4 ways with 2 pinks, 4 ways with 2 greens. So I could get 2 equal colors in 12 different ways out of 20. So that 60% of the times I should get 2 same colors. So Bell said, well, let's do this experiment. So 60% of the time I should get 2 same colors. And he did this experiment many, many times. And many other people did the experiment too. What's the number we should get? 12 out of 20, that would be 60%. But what we got was much lower, 55%. Way beyond the experimental error. Much lower than experimental error could be 2%. So if we are supposed to get 60, and if it gets 58, then we are within the experimental error. But this is way beyond the experimental error. Something is happening. So the quantum physicists are right. These things are communicating with each other. When we have 3 here, I got 3 here and 3 there, and I send these to Iceland and I keep it in a box. Once it is gone to Iceland, I check. Pink right. And then pink right would send a signal to the one in Iceland. Hey, I'm pink right. You become pink left. And it becomes pink left. And there are no white ones here. Then I got 2 green ones, and then got the 2 white ones. So that's the only way. They have to communicate with each other at long distances. If they do not communicate, then we should get 60%, like in the case of socks. But we don't get 60%. We get much lower. And the numbers that we get are predicted by quantum physics equations. So this is called spooky action at a distance. Quantum entanglement. They're entangled. So all kinds of theories out there. There are strings, vibrating strings. They vibrate, and this one and this one, there's a string there, okay, and they vibrate. So if we make a measurement, the string stop vibrating, and this would collapse. The wave function collapse. This is the string theories, and there are all other theories, but nothing really that everybody agree upon. The main point is that they communicate, one, and they communicate instantaneously. They communicate faster than speed of light. If they don't communicate, what's the number we should get? 60%. If we are not getting 60%, because 12 out of 20 times we should get 2 equal color socks. But if we are not getting that, they have to communicate. That's the only explanation. There's no any other explanation. Even though they are other side of the universe, they have to communicate in an instance. Extremely faster than the speed of light. It's spooky action at a distance. That's what Einstein said. I hope you understand the Bell inequality and Bell experiment and Einstein Rosen Podolsky paper. Basically, that's the nutshell. There's not more to it other than the quantum physics math there, but the conceptually, that's it. That's the whole idea, conceptually. If we do these things with socks, we should get 60%. But if we do this with electrons, we don't get 60%. It's much lower because electrons do communicate. That's the explanation, and that's Bell experiment. Thank you very much.